Hi and welcome to this new video in which I continue my Linux Privilege Escalation series. In this video we will focus on a specific type of exploits which are known as binary exploit. So we're going to talk about binary exploitation and I will show a really simple example of a buffer overflow on a 32-bit application. So essentially we have this simple application which is vulnerable to a buffer overflow because of the way that the strcopy function is used. Here essentially we are copying from the char input, from the buffer input to the buffer as a local variable. We are copying the value, but we have no check to make sure that this pointer points to less than 512 bytes. So this is a typical buffer overflow situation and we can exploit it. I will show the assumption we will be working with, an analysis with GDB, and the final exploitation step. During the video, I will also be working on a Kali Linux machine, this one, where we have all the laboratory to show the buffer overflow. So here we have the vulnerable.c, here we have the genpayload.py, which will be a Python script used to generate our final exploit, and here we have another shellcode.c example. So we can compile the program with this gcc command. Notice that it has a bunch of different flags, and these flags are used to remove certain protections. The objective of this video is not to introduce to you modern binary exploitation that bypasses all the modern mitigation, but rather to just give you the intuition, the idea behind binary exploitation, and why it is important to consider in the context of privilege escalation. So we can compile our program, and if we just execute the compiled program, look at this now, we have vulnerable.c, which is the file I showed previously. It's a simple file, and then we have compiled it into the ELF binary. It's an ELF 32-bit binary, and we can execute it. So we execute it. Of course, notice that in the main function, we check the arguments. If the arguments are not greater than 1, we do not do anything. That is, we only execute the vulnerable function when we have at least one argument. Actually, at least 2 arguments, because the name of the program is always the first argument in the argv array. So if we put, for example, AAAA, we execute it again. Now we trigger the vulnerable call, so this code actually is executed, the vulnerable here, but still notice how nothing happens. Even if we just do it with a longer argument, we can keep sending stuff, but essentially nothing happens. And why is this the case? Because when we call vulnerable, when we reach this function, we have a certain input, which is a pointer to a char. So essentially this points to our arguments like AAAA. So specifically, it's this string in the memory of the program, right? And then we just perform a stir copy. And this stir copy takes the memory from the source, which is the input, and copies into the destination, which is this buffer. So this is the output. Now here the vulnerability lies in the fact that this output has a certain fixed size, which is 512 bytes. However, no check is made to be sure that the input is less or equal to this size. This means that it is possible for me to give, let's say, a 1024 bytes input, and what happens is that I will run out of space in this buffer, so all the memory for this buffer I will run out of space with a bunch of A's, and then essentially what I'm gonna overwrite in the memory is I'm gonna overwrite critical control structures that are used by the processor to handle the control flow of the program. And we can see this in action, how? By just calling the binary with a very long string as input. So let's put like a lot of A here. Let's put like even more than this. Let's put like a lot. And notice what's happened now. We get a segmentation fault. We get a memory error because the processor in the execution, it executed this string copy. So it copies this huge string into the memory, and this overwrote all the memory for the buffer, and then it went overboard. It went into an overflow. So that's the idea. When we have binaries like this, which look like they do nothing, like in this case, but are actually vulnerable to memory corruption vulnerabilities such as buffer overflows, sometimes it is possible to take these binaries and use them to hijack the control flow of the program in order to introduce malicious code. In this case, for example, we will develop a very simple payload, a very simple exploit essentially, and we can see the bytes of the exploit in this payload.bin file. If we just analyze these bytes, we will see essentially, we can do this with the flag B, so we get all the bytes of the payload. We see a bunch of bytes 90, so all of these are like 90, 90, 90, 90. Then here we see a bunch of different other bytes, and at some point we see a bunch of bytes repeated, E0, D4, FF, FF, E0, D4, FF, FF, repeated many times. So that's the general structure of our exploit, and in this video I will show why we built it that way. Now, what can we do with this sequence of bytes? Well, the idea is pretty simple. So we said that this binary is kinda naive, like it just does nothing, right? But in actuality, it's really pretty dangerous. If we give in input this payload, we can do this with this flag, with the shell substitution syntax. Notice what we get now. We get a shell. We get a shell as the user who was executing this program. And so a binary that at first glance is not really that dangerous can actually be used to execute arbitrary payloads with a shell. For example, in this case, can execute UMI, ls, and so on and so forth. Now, of course, in this specific case, we obtain a shell as the user Leo, because the process running the binary was executing at this particular user. Now, this can be more dangerous, for example, if we have a root-owned SUID binary. I've already made a video describing the SUID exploitation. For example, if we have a binary that is owned by root and that it has the SUID bit on, then once we're able to hijack the control flow of the program and we're able to introduce arbitrary instructions, we can just execute a set with D to 0, and then we can execute a bin sh, and we will obtain a root shell. So essentially, this can be extremely dangerous depending on the configuration of the system. And all of this is to say that another road that brings us to privilege escalation in a Linux system is the exploitation of specific binaries of specific programs. Now, typically, this is an hard path to follow, because in this video, I'm gonna really show a simplified version, a simplified exploit. Typically, modern binary exploitation and research is really hard. However, it is important to understand that this path exists, that binaries can be hijacked, that the control flow of a program can be hijacked, and I will show a simple way of doing it. So, I hope the video is enjoyable, I hope you get something out of it. If you do, leave some feedback, subscribe to the channel, and share this with like-minded people to help me grow. Thank you and enjoy the video. So we already saw the code essentially, I already discussed it. Here we have a bunch of C libraries, here we have two functions, a main and a vulnerable. The main makes sure to call the vulnerable when we have at least two arguments, and here the check is made on argc. Now when we run the program through the shell, for example in this syntax, we do -- name of the program and then the input. This array of arrays, it's sort of like an array of strings, is filled up with these arguments. So the first element is going to be the name of the program, /vulnerable. The second is going to be the AAA. And of course, remember that in C, the arrays are indexed from 0. So this is going to be index 0 and this is going to be index 1. This means that when we check the argc is greater than 1, we are checking that there are at least two arguments, and then we're giving to the vulnerable function the second one, which is this AAA. So to the second one, the input is going to point to the AAA string here, and then we will simply perform a str copy. So str copy is used to copy memory from one location to another location. In this case, we have a buffer which points to 512 bytes of memory. This is like uninitialized, so it could contain anything that was in memory, and we want to copy it. Essentially, we want to say, okay, now I want to copy this string into the buffer. The problem arises when the string we are copying is way too big compared to the destination buffer. If this is the case, then we will copy the entire string, we will finish the size of the buffer, and then we will overwrite critical data that is used by the CPU to handle the program. So this is the program. Now to compile it, we actually have to use various different flags. Let's review them. So the -o is just to specify the name of the output. Here is just the name of the source code, vulnerable C. The -g is to add the debug information to the build, so we can debug it with GDB. And then these different flags are used to, so the -m32 is used to do a 32-bit compilation. So why 32-bit? Well, the idea is that 32-bit application and 64-bit application works differently. 32-bit is a bit simpler just because the addresses have less bytes. They only have 4 bytes because we are working in a 32-bit memory, essentially. But honestly, even in 64-bit, it's not like it changes so much. I mean, some things change, so it's a little bit easier to do buffer overflow exploitation in a 32-bit system, but many of the ideas, they carry over to 64-bit with certain adjustments. So that's the idea. We compile it and then we execute it. So the question is this program safe? So is this program safe? And the idea is that no, it's not safe, because it suffers from a very well-known memory corruption bug, which in this case is the buffer overflow. How can we notice it? We just give the program a big enough input, long enough that it will finish the space we have for buffer, and it will overwrite the critical sensitive area after the buffer, and then we get a segmentation fault. So if you have a C program and you give it certain input and you get a segmentation fault, most likely you have a memory corruption error. This should not happen in a safe program. If you get a segmentation fault, something has gone wrong and it could be dangerous. So this can be considered a vulnerability. Of course, to go from vulnerability to binary exploit, it takes a lot of research and a lot of work. It is all about making sure that the condition that this bug arises are completely controlled, and they are controlled in a way to not only crash the program, we don't want a crash, but rather we want to hijack the execution of the program into a new direction. So if the program was going its own path 1, we want to introduce an input that makes it go astray, but then we want to control where it goes to obtain a code execution, to obtain a code exec. So this can be very hard to do. In this video, I will show a really simple example. So this is not modern binary exploitation. It's extremely simplified just to make sure that it's okay for this series, because this series is about I would say initial content on Linux privilege escalation. So it's good to talk about buffer overflows. Specifically, why is my approach simple? Because I make a lot of assumptions. So in this video, we will analyze a very simple exploit. This is because we assume to be working in a very simple model that does not have the protections that modern systems offer regarding memory corruption. Now, these protections in particular are the following. We do not have a non-executable stack. This means that if you consider the memory for a program, it is divided in various sections, and the stack is the area of the memory, the region of the memory, the section of the memory where local variables live. For example, if we go back to the code, this buffer variable lives in the stack frame of the vulnerable function. So the stack frame is created every time the vulnerable function is called, and in the stack, if this is all the stack, right? If this is the stack frame is a chunk of this stack. This is the stack frame of vulnerable. If you call other function, you will have other stack frames. Well, typically what happens is that in modern binaries, the stack is non-executable. This means in particular that when the CPU tries to fetch instruction from this particular memory, from this particular region, it will get an error. It will throw a sort of exception, because it will realize that it's fetching instruction from the stack area, and the stack is non-executable. You can configure it to remove this protection, and we have removed it through this, essentially this flag, -z exec stack, which means make the stack executable. Another memory protection is that we have no canary value. Now the canary value is used after the stack frame of a function, so it's like a special value here, is called canary, and it makes sure that in the context of a buffer overflow, the buffer overflow would naturally also overwrite the canary with a new value. Well, after the function is over, the canary is checked to make sure that no one has overwritten it, and if someone has, then the control flow is interrupted because a smash stacking attack has been intercepted. So the idea is that if you modify the canary through a buffer overflow, the operating system realizes that and does not make you go forward with the attack. So this is another thing, and we remove this with the flag here, with the compilation flag -f no -stack -protector. So we remove the stack protector, which is the canary value. Then another thing, another assumption we make is that we work in a 32-bit architecture. This is not like it increases or decreases security, it simply changes the way things work. In a 32-bit architecture, for example, the arguments are passed to the stack. So when we call a function, like for example the vulnerable function, these arguments are all passed within the stack. While if you use a 64-bit architecture, for example, the arguments are passed through CPU registers. So this is the idea, but honestly it does not change too much, this change from 64 to 32. It's just that to simplify, 32-bit architecture have just less bytes per address, it's a little bit simpler. And finally, this no ASLR, essentially. This has to do with the randomization of the addresses. So in modern Linux programs, essentially, every time the program is executed, the kernel randomizes the layout of the memory. It means that the position of the stack will be random for every execution. All the addresses within the stack start from the same offset, from the same base, sort of, but the position of the base will be randomized at each startup. This protection is useful against exploits that makes use of specific memory addresses. Like if you say you have this function in memory address 0xFFFF D788 or something like that, if you use an hard-coded memory address with ASLR, the exploit won't work. To simplify things, we will disable it. To actually disable it, you can write into the kernel file /proc/sys/kernel/randomize via space. You can write the value 0, and this will disable ASLR all over your system. So be careful, only do this in a test system like a virtual machine, because it could be dangerous, it could decrease the overall security of your system. So while the basic idea behind binary exploitation does not change if we are in 32-bit or in 64-bit, if we have the canary on or the canary off, if the stack is executable or not, so the basic idea is the same. However, what changes is the way in which it is performed. And the way in which it is performed nowadays in modern system is drastically different, as one has to deal with all of these new protection and countermeasures and mitigations. For example, if you have SLR activated, to actually use addresses, then you need some sort of like address leak to understand where things are within the memory layout and things of the sort. I mean, for every protection, there is a countermeasure most of the time. It's just that it adds the complexity and sort of like the constraint with which you are working with. So making assumption in this case simplifies our life. And these are the assumptions I made. So we can get out GDB. I've already made a video on GDB, so go check that out if you have no clue about GDB. I will not talk too much about the tool. I will just assume you know how it works. If you have no clue, as I said, go check out my previous video where I discuss how to use it. So we have loaded the binary GDB. The first thing we can do is just list out the functions. As we can see, we have two functions in the vulnerable.c file, which are main and vulnerable, so nothing new there. At this point, we can check out the code for the main function, and I'm not talking about the source code, because we can already see that actually. I mean, this is the source code, so nothing new there. I'm talking about the assembly code, the code that is actually executed by the CPU. How do we get that code? We can use the disas function of GDB. So we can do disas main, and this essentially is the code for the main function. So the interesting things of this code are, as always, the typical, the initial of every function is a prologue. This is the prologue, where we just create space in the stack for the function. Then we call something regarding x86. I'm not sure if this is for 32-bit compatibility, not really sure about that. And then we start to check for the argc value. We check if it's less than 1, jump less equal, is jump less equal. And if the check goes through, if it is not equal, then we do the call. So we do this push, and then we do the call to vulnerable. So here we push the value of the register into the stack, and this is the first argument of vulnerable. And since vulnerable only has one argument, we just call the function vulnerable. So we don't need to care about the details of all the other assembly code. Here the main idea is that, look, we call the vulnerable function, and then after the vulnerable function has finished to execute, we will come back to the main code starting from this like address, starting from the instruction main plus 51, this add esp 0x10. So that's the idea. So this is the code for main, and we can do the same for the code for vulnerable essentially. So also for vulnerable we have the prologue here, these first values, and then essentially we have the call to the string copy. So here we get the arguments from the stack, and then we have the call to the string copy, and then essentially we have the return final value. So that's the idea. Very simple assembly. I mean, we will not delve into the assembly. This is not going to be a video about assembly. I can make later a video about that. What we are interested in is the main flow of the program, and it's really, really simple, as we can see from the code itself. Now let's do a run of the program, but when we do a run, I want to check essentially how the stack changes depending on our input. So in particular, I will be interested in putting a breakpoint in this, before this particular instruction, before the call to the str copy. Why? Because before the call to the str copy, the stack is valid and it has all the bytes that typically it has. After the call of str copy, we will have copied our long string, all the bytes, which means that we will have disrupted the stack structure. So I just want to understand how it all works. I can put a breakpoint with vulnerable plus 35 with this wildcard, with this asterisk to reference the address here. And then I can say run. So here I run. Notice that if I do this as main again, the address I get here are different from the initial address that I got here. This is because at this point the program was not loaded, so these were the static address present in the elf binary file. After the process has been run and loaded, so like loaded and executed, this address get loaded into memory, so they change. And specifically, the return address of the vulnerable call, which is the address after the call to vulnerable, before it was 0x0000. Now it is 0x565561f4. No, actually it's this one, f1. So it's like 0x565561f1. Now, why is this address important? Well, consider this. If we disassemble the vulnerable code here, we have no information regarding the place in the code where we have been called. I mean, if you consider a point of view of the CPU while it is executing the instruction of vulnerable, like let's say here, this function, the CPU has to know where to go back, right? Because it's going to execute all these instructions, and then at some point it's going to do, okay, now I return to the place I come from, right? So we were called in main. After vulnerable, I have to go back to main. I have to go back to the function that called me. Now, where is this information saved? This is a critical question, because depending on where it is saved, a malicious attacker could manipulate that return value, could manipulate that address that specifies where execution should return to. Now, where is this variable stored? It is actually stored in the stack. And we can see that how, well, first of all, how we can analyze the memory of the stack. We can use the GTB command X. We can do, like, for example, X 10 WX $ESP to get the no register. I think it's because it has to run. So, okay, it has to run with some arguments like A. Now I am in the breakpoint, and now I can analyze the stack memory. So in this case, I'm reading 10 words, which is 10 sequence of 4 bytes each, starting from the register ESP, which represents the end of the stack. So essentially the stack starts at a given address, and then it grows downwards towards higher addresses. So essentially, you can say that actually the stack grows towards lower addresses, but when we read it from a given address towards higher one, because we are reading the previous stack, all the stack that exists so far. And it grows, it expands towards lower addresses. So for example, in this case, I'm reading 10 sequence of 4 bytes each, starting from the address 690 towards 680, towards 6B0, and so on and so forth. Now, to actually understand where this saved address it is, which is actually this one, to actually see this saved return address, we can just read enough bytes from the stack. Like for example, in this case, 128 should be enough. And if we just check this particular number, we just check it among here. So let's see. Okay, there is no such number, so we probably have to check a bit more. So let's say 138. Notice that what we got now. We got, essentially, at the end, so technically the last one is 136. We just care about 136. But notice this value, which is present in the stack, because what we are seeing here is all the memory present in the stack. At some point in the stack, we see this saved value. This saved value represents exactly where the processor will look for to understand where to go next after the vulnerable function has been executed. So this means the processor executes all the instruction here in vulnerable. At the end, the last ret instruction simply reads this value from the stack, and it starts to execute the next instruction from this particular address. So this is where the concept of control hijacking comes in, because if you're able to do a buffer overflow, if you're able to overwrite all these bytes, and you're able to change this saved return address to an arbitrary value, we will be able to control where, like, the CPU goes back to fetch new instruction. So essentially, that's the idea of our exploit. So this is the state of the stack before we write any value. Let's write the value with the next instruction, and let's read once again the state of the stack. Notice that we wrote a bunch of 414141 bytes here. So before, let's see, so before the address 680 was empty, 0000, now it contains 41, 0x41, 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 which in hexadecimal, this is just the ASCII encoding for A. So since we write AAA, we got the 414141. For example, if instead we were to do AAAA, BBBB, CCCC, DDDD, and we run again, we check the state of the program, of the stack before writing, we write with the next instruction, we check after writing, notice how it changed. So before we had all 0 here, and now we have 414141, 424242, 434343, 444444. So we can control the memory that is written starting from this address. Now with this view, it's also easy to understand why buffer overflows can be dangerous for a program. Because what's the idea? Well, the idea is that remember that this value at the end here is an important one because it is used by the CPU to check where to go next. But if you're able to write this value up here, and if you're able to write more bytes, which means that we're gonna write the third row, the fourth row, and we're gonna write all these rows, all these rows, all these rows. If there is no check on our length, if we can just keep writing and writing and writing, if there is no boundary check, at some point we will be able to write a value exactly here. And when we change this address, it is exactly when segmentation fault happen. It is when we change this address to an invalid address. What happens, however, if we change this address, but not to an invalid address? What happens, for example, if we change this address to an address that points to the stack? Well, this is exactly what we will do. And to quickly compute how many bytes we need to write in order to overwrite this save return address starting from our position in the stack, which is this address, well, what we can do is we can start from this address. And what's the address of this value? Well, we start from the column, which represents the address of the first column here. It's like this address, the FFFFD890 is the address for this. We add 4 more bytes we get here. We add 4 more bytes we get here. We add 4 more bytes we get to the start of this one. So the start of this is the address, the value, this value with the C at the end. So if we just check one word of memory from this address, we get essentially the saved return address. We start from this, and then we simply subtract. We do print decimal the initial one, which is this one, which is this value. And notice we get 524 bytes. So we have 524 bytes if we want to overwrite the return address. So let's check our assumption, right? How can we do it? Well, for example, we can compute with Python. So Python C, I can do print A times 524 plus B, so 4 B's. And I get a certain string, I get this particular pattern. Then I can run the program with this particular pattern. I can write into the stack with next instruction, and I can read the content of the stack. So notice that I was able essentially to write everything, but now here the save return instruction is for true, which means that it is no longer valid. If I now continue the execution, it's gonna say, look, program has a problem, a segmentation fault, because he's not able to understand the instruction. Like this address does not point to anywhere in the system, and this is a problem, and so we have a segmentation fault. But what we were able to do is show that we're able to control exactly the value that we write into the return address, which is a critical point in binary exploitation of this type. Now, the particular exploitation technique that I will follow is to use a so-called NOP sled. So essentially the idea is that the processor has different opcodes which define the kind of action to execute upon reading an instruction. So when we have an opcode of 0x90 and the CPU reads this instruction is called NOP because it stands for no operation. It means essentially do nothing. Process the instruction, but do not take any action whatsoever. It's called a NOP instruction. So the idea is to use this NOP instruction as padding. Now, why they are useful? What's their usage? Well, the idea is that we want to write into the return address an address in the stack. But the problem is that we also want to write a specific shellcode, which we will discuss in a bit what it is. The shellcode essentially is just binary instruction that the CPU will execute. Now the problem, however, is that if we jump in the middle of the shellcode, this will break the logic of the shellcode and therefore will make our exploit not work. So we want to start execute the shellcode from the first instruction of the shellcode. This means that we need to know exactly where the shellcode will be in the memory. And this knowledge sometimes is really hard to know. So what can we do instead? The idea is just to have a return address which is roughly around the shellcode area, but not exactly to the start of the shellcode, as long as it hits the NOP sled, which is made of all 0x90 instruction, which is the 0x90 byte. So as long as we hit one of those NOP instruction, we will go down the NOP instruction, we will keep executing them until we hit the shellcode. And so with this setup, with the usage of the NOP sled, it's gonna be easier to hit and run our shellcode. So essentially this is the idea, this is the stack, this is where we'll start write. We'll write a lot of NOP sled, then we will write our shellcode, and finally we will write a lot of new return address. This is just the same address repeated, and this address will point to the stack area and hopefully to the NOP sled. We will do a little bit of guessing to guess this new return address. Of course, for example, in this case, we are assuming no ASLR, because if there was randomization, then this new return address could not be computed by hard coding it into the exploit. It would have to be computed at runtime depending on the specific application. So it's like we are simplifying our life here. And so that's the general idea. Now, to continue going forward, we need to talk about shellcode. So roughly, what is the shellcode? To understand the shellcode, we can see this simple example in C. I actually do not remember where I took this shellcode. I did not write it on my own, but I forgot where I took it. So if you remember, if you recognize it from elsewhere, please write to me in the comments and I will put a reference in the description. So forgive me for that. But essentially, the idea is this. The CPU, when the CPU executes single instructions. Now, typically, these instructions are wrapped into binaries, like for example, ELF binaries. And the ELF binary is just a wrapper around the code and the data. Now, when we talk about shellcode, we're just talking about raw code that the CPU will execute. So if the CPU starts to execute this first instruction, it will understand how many bytes to read, and then it will decode the instruction, interpret it, and execute it. And this is all to say that the shellcode is a byte representation of the code that can be executed by the CPU. We put this in memory, we inject this into memory, we point the CPU to execute that code, and then we have our code execution. So the idea is to introduce code execution through the usage of shellcode. So this simple C program defines a shellcode as an unsigned char, then we print out the length of the shellcode, and then using a function pointer, we executed the shellcode. So how can we compile and test it? Well, the idea is that we can open a new shell, we can go into tmp bof, we can compile this shellcode, so we have the shellcode, and we can test it out. If we execute the shellcode, we get a simple shell. This is the same payload that we have obtained execution when we do cat payload.bin. Because at the end of the day, the idea of our exploit is to introduce within the memory of the vulnerable process exactly the following shellcode. And if you look at the payload itself, if we just look at the payload, like in here, extamp cv payload.bin, and we make it more readable, we see that after the NOP sled, so let's see here, so the NOP sleds ends roughly here. And then we have an EB1F5E89. And notice the shellcode here, EB1F E589. Of course, since this is C, in C, the raw bytes are written such as /x and then the byte itself, the hexadecimal representation of the bytes. So so the first thing is EB1F, then continuing 89. After we have, so like EB1F89, then we have 768031. So 768031. So these 3 bytes correspond to these 3 bytes of our exploit. Because the structure of our exploit, as I said, is we have the NOP sled, which is all these 90 bytes. So this is all the NOP sled. Then we have the shellcode. We have the shellcode. And at the end, so this is all the shellcode. And then we have the new return address. So the return address that we use to overwrite the old return address, and this value will be used to hijack the control flow of the program. Now, how can we generate this payload? There are many ways of doing this. I will show a very simple way using a Python script. So this is a Python script that uses Python 2.7. This is an important difference, by the way. It's not Python 3, it's Python 2.7, and this is because of the way that bytes are handled in Python 2.7. If we execute this script with Python 3, it's gonna complain. It's gonna say, you cannot concatenate a string to bytes. If we do it with Python 2.7, no problem whatsoever. So this is really good. So Here I use the struct, and I don't even think I use the sys function here, so I can remove this import. So I just use the struct library, and this is used to pack stuff, but I will talk about that later. So this is a simple guard to execute main only when we call the script from the command line, and this is the main function. So here I define a bunch of things. I define the shellcode taken directly from the shellcode.c file. So just copy and paste the shellcode and it works. Here I have the offset, which we computed manually by taking into consideration the amount of bytes that exist between. So let's do a run here, simple run. I do a run here, and then I do next instruction, and then I print all the stack to make sure we see the return address. So this 524 or 26, what is it, the value is 24, was obtained by understanding how many bytes separated the saved return address, which is saved here in this, from the first address of the stack that we can write to. How did we get this number? We just printed this value with the final letter, not 0 but C, because the 0 is for the first column. For the last column it's C, minus this first one with 414141, and this equals to 524. So this is the offset value we use, and then we have the amount of times we want to write the new return address. And then we find the return address. So this value is hard-coded, and this means that this only works because we have disabled ASLR. If I enable it again, it's not gonna work because this address is gonna change every time. Now, how did I obtain this address? Well, a bit using GDB and a little bit by trying with simple values. So the idea is that with GDB, we get roughly where the stack area is when we debug the program. For example, we know that ff d something, we're probably around this area. Now, the particular number after d, however, I picked manually. Why? Because when we use GDB, we are modifying a little bit the memory layout, the memory area. So the stack is a bit different, which means that without GDB, few numbers, the few remaining numbers of the stack could change. I just moved a little bit. I tried 5, I tried 4, and 4 worked, and that's it. So like the idea is you pick a number with GDB, and then you try a bunch of values manually to see the one that works. You can also write a little scripts that automates this stuff. This is not really important for now. It's just to show that you need this kind of information. But in this way, in this naive way, this only works because we have disabled ASLR. Then we actually write the payload, this buffer value. So this is where the payload we write, and this payload is then written into the payload.bin file. Remember to open this file in a write mode because we need to write stuff, and also in binary mode because we need to write raw bytes. So that's it. And with respect to the payload, it's really simple. First, we write the NOP sled, then the malicious shellcode, then we write some more NOP instruction to make sure that the new return address value is properly aligned in memory, and then we write the new return address. Now, why do we do this thing, this memory alignment? Because, for example, if the shellcode ends, but it is not really aligned in memory, so for example, let's say it ends here, it means that the final byte of the shellcode is here. The new return address is going to write these 3 bytes here, and then a single byte here, and this is going to totally mess up the memory. So it's not going to work, and we're not going to be able to control the return address, because the return address has to be aligned at a specific offset in memory. So we just do this to make sure that it is aligned. So essentially, that's how it works. We can just execute it. So we can just remove the previous payload. So I remove payload.bin, I execute with Python 3 the generation of payload, and then I try it with the vulnerable program, payload.bin. So let's see, where is payload.bin? I do cat payload.bin, and notice that I have a working shell. So for example, in this case, I have enabled once again ASLR, just to show that now it will not work. Randomized via space now is the value true, so it is enabled again. And if I try the exploit, it's just gonna give me segmentation fault. To make sure it works, we have to disable it. If I disable it, like this, with echo 0, proxies, kernel, randomize via space, and I execute again, notice that it works. So make sure if you try this on your own that you have disabled ASLR. With respect to this return address, use GDB, understand where the stack lives, and try to guess the last values here, the low-end values of the address. Like just try with the one right after the this thing, the FFFFD, and it should work. So this is the idea. We can sort of like hijack the execution of this program and obtain from a process that would not do much, that would not do anything, we can obtain a full shell. And with this shell, we can do anything we want. So essentially, that's the idea. And in here, you can find the script for the generation of the payload and the final payload itself. So if you have any problem trying this on your own, just write in the comments and I will try to support you. So what are the takeaways to conclude this video? The idea is that while the binary exploit shown in the video is extremely simple, the same idea can be applied to modern binaries with all the latest protections. Indeed, all these protections with enough work by researchers and with certain assumptions, sometimes it happens that this protection can be bypassed with appropriate techniques and primitives. Which means that the biggest takeaway is that sometimes the binaries present in a system can be vulnerable to binary exploitation for a variety of reasons, including memory corruption. This in turn can make it possible to hijack the execution flow of the binary in order to execute arbitrary code, including malicious code. And this means that exploitation of user space programs can also be a path towards privilege escalation. And here at the end, I use a specific word. I said user space programs. So what I showed today was binary exploits, binary exploitation of user space programs. The idea is that, is there another type of binary exploitation? And actually there is. It is the exploitation of kernel programs, of kernel binaries, of kernel space code. So not really kernel binaries, but of kernel space code. So that's the idea. And in the next video, which is going to be the final for the Linux Privilege Escalation series, we will see some practical example of kernel exploits to discuss more about this idea. So I hope the video was enjoyable. I hope you got something out of it. If you did, leave some feedback, subscribe to the channel, and share this video with like-minded people to help me grow. And that's it. To the next video.